Welcome! This is the second tutorial of a three-part series on how to get started with the gas turbine performance software, GasTurb. The tutorial series provides an introduction to GasTurb's user interface and its most frequently used features. A basic understanding of gas turbine performance calculations is recommended to make best use of the software and follow the tutorials. In this tutorial, we will learn how to perform design parametric studies in GasTurb. We will vary either one or two gas turbine design parameters and visualize the influence of these parameters on its performance in different diagrams. We will further customize the diagrams, adding contours as well as parameter limits. Finally, we will combine parametric studies with user-defined iterations. With these tools, GasTurb enables us to answer a wide variety of gas turbine design questions and discover interesting relationships between design and performance parameters. For this tutorial, we select the two-spool turbofan configuration with an unmixed exhaust. The main window appears with the demo data loaded. The performance scope is already selected, and we continue to the design point input window. The design point window appears, which we already explained in detail in the first tutorial. We leave all input data with the predefined values and conduct a design point simulation as a reference point for our parametric study. Click on Design Point. The calculated cycle is set at cruise conditions with 11,000 meters altitude and a Mach number of 0.8. The overall pressure ratio is rather low at 17.33. The burner exit temperature is 1,450 Kelvin and the bypass ratio is 6. This cycle is typical for a small business jet engine. Let us return to the main window. When we set a gas turbine design point, we select the compressor pressure ratio and the burner exit temperature, among other parameters. A good understanding of how the cycle is affected by these parameters is very valuable. With parametric studies, we can examine and visualize the influence of varying either one or two parameters on the gas turbine's cycle. To conduct such a parametric study, we click on the task Parametric. In a parametric study, GasTurb will conduct several design point calculations, all with the same input data, but altering the selected parameters whose influence we wish to examine. These parameters are selected in the parameter selection window. We select the high-pressure compressor pressure ratio as the only parameter for our first study. Now we have to define the interval and the step size of the variation of the pressure ratio. We choose a start value of 5, a number of 5 values, and a step size of 1. The displayed reference value is the value of the previously conducted design point calculation. Now we run the parametric study. The result of a parametric study is presented graphically. In the output window, we can define the plot parameters for the output diagram. By default, specific fuel consumption and net thrust are selected as the plot parameters. The diagram shown is only an exemplary representation and does not already contain the desired values. To assign the overall pressure ratio to the x-axis, we drag it from the selection tree to the field at the x-axis. Afterwards, we click on Draw. The results of the parametric study are displayed for the assigned axis parameters. Each yellow square marks a design point calculation conducted for a different high-pressure compressor pressure ratio between 5 and 9. The initial design point calculation is marked with a black square. We can see that with a higher overall pressure ratio, the specific fuel consumption is reduced. Let's continue and add further parameters to the diagram. To do so, we click New Picture. We can select up to 4 y-axes and drag the high and low pressure turbine pressure ratio as well as the low pressure turbine exit temperature T5 to the y-axis fields. Afterwards, we click Draw. The diagram with the 4 ordinate parameters is displayed. The curves are differentiated by the color as well as the symbols of the plotted points, which are displayed on top of each axis. We can see that when the overall pressure ratio increases, the pressure ratio of both turbines increases as well. Therefore, as the burner exit temperature, T4, is not varied in this study, the exit temperature of the lower pressure turbine decreases. Let us return to the main window and start another parametric study in which we vary the burner exit temperature T4 as well. For adding a second parameter to the study, we click on the Second Parameter tab and choose the burner exit temperature. We define 9 values, starting from 1400 Kelvin with a step size of 25 Kelvin, and run the parametric study. Now we plot the graph specific fuel consumption over net thrust. For each combination of the varied parameters, a design point calculation is conducted. ISO lines connect the design points calculated for the same input parameter value. Thus, the intersection points of the ISO lines represent the calculated design points. The black square again marks the initial design point calculation. To display the output window of a specific design point, we click Details and select one of the calculated cycles. Let's choose the combination T4 equals 1425 Kelvin, HPC pressure ratio equals 9, and double-click. The design point output window is then shown. There we see the prescribed values of T4 and the HPC pressure ratio. To plot a third parameter, a contour plot can be used. We select the parameter core efficiency, drag it to the contours field, and draw a new picture. Colored efficiency contour lines are now added to the diagram. The contour parameter is indicated on the top right corner. We can customize the layout of the contours via Picture Format, Steps, and Colors. When choosing gas turbine cycle design parameters, we have to keep many limits in mind. To take such limits into account when conducting a parametric study, they can be visualized in the diagram. Let us create a new picture. In this case, we will define the inlet temperature of the LP turbine as a limiting factor, for example, due to the turbine material. We select the LP turbine inlet temperature as a limiting parameter by dragging the parameter into the field in the Boundaries tab. We add the value of 1200 Kelvin, define it as an upper limit, and draw the new picture. The gray-colored area marks the value range that exceeds the limit that we just defined. The limited parameter is displayed on the top right corner. Let's draw another picture. This time, we create the diagram of the specific fuel consumption over the ideal jet velocity ratio. The ideal jet velocity ratio is the relation between the ideal bypass nozzle velocity and the ideal core nozzle velocity, who are each calculated from an isentropic expansion to ambient pressure. As analytics show, for the optimal design of an unmixed engine, the ideal jet velocity ratio reaches a fixed value related to the LP turbine and fan efficiencies of the jet engine. In this case, it is apparent that the lowest specific fuel consumption is achieved if the ideal jet velocity ratio is approximately 0.8. The jet velocity ratio can be influenced via the outer fan pressure ratio, So, let us conduct a parametric study where we iterate the outer fan pressure ratio in such a way that the ideal jet velocity ratio is equal to 0.8 for all cycles. Thus, all the cycles are optimized for a low specific fuel consumption. We return to the Design Input window and go to Iterations. We choose the outer fan pressure ratio as an input variable, define the minimal value 1.1 and the maximal value 5, and select the ideal jet velocity ratio of 0.8 as the target value. Finally, we activate the iteration. Now, we can rerun the parametric study. Let us draw the diagram with axis, specific fuel consumption, and net thrust. We can now observe the parameter trends with an optimized outer fan pressure ratio. Let us open the detailed output window of the parameter combination we already had a look at without the iteration. As we can see, the iteration succeeded, and the ideal jet velocity ratio of 0.8 could be achieved. Comparing the results to the previously calculated cycle, we can see that the specific fuel consumption has been reduced by decreasing the fan pressure ratio, as we expected. In this tutorial, we learned how GasTurb's parametric studies simplify our engine design process and help us discover relationships between design variables and performance results. Now, good luck designing your own engine with GasTurb, and let us know if there are any questions left. In the next tutorial, we will learn how to simulate the engine performance under off-design conditions.